Welcome back. In this video, what I want to talk about is the complex power that's actually supplied by the source. And in this case, this is our source that we're investigating. And maybe you recognize this circuit. We've actually seen it before, but here I'm allowing for the different elements to be already identified, and we have a line, a transmission line impedance consisting of a real part of 2 and an imaginary part of J1, and then we have our load on the right, or the vertical piece, and I'm denoting that with a voltage of phasor of V sub L bar, and it's now comprised of a real part of 78 ohms and an imaginary piece of Jx sub L, where that's J59. And what we want to do is we want to find the complex power that's being either absorbed or supplied by that source. And we need to now determine, is the power absorbed or supplied? And we can go back and try to refresh our memory on the passive sign convention. And here's the picture that we've been using for our passive sign convention. And it really says that we can associate a positive sign with the V voltage phasor times the complex conjugate of the current phasor if the current as it's defined, which in this case is flowing from left to right, if that positively defined current is going into the positive terminal of our element prior to the current flowing through the element, then we associate with that a positive sign, because then power is absorbed by that element. And that's the passive nature of this notation, or that's why it's called the passive sign convention. So we're defining the passive sign convention in this way, and that means we put a positive labeling on VI star when the defined current flows into the positive terminal before that current flows through the element. In our particular case, or in this quiz, you probably have seen that circuit also in the quiz, we want to know what's the associated power of the source. Is it absorbed or is it supplied? If we look at this particular way that we've labeled this example, you'll see that the current is actually already passed through the generator or the source before it then goes or touches the positive terminal of that source. The current is not flowing into the source prior to it going through the element or the source generator. So in this case, the power is absorbed. The power absorbed by the source is actually a negative product of the voltage phasor times the complex conjugate of the current phasor. So in this particular case, we could say the complex power absorbed by the source is minus V sub S bar I sub S bar star. Or if we don't like that negative sign, then we could say, we could reword it and say that the complex power supplied by the source, in fact, the way that we've labeled the voltage and the current, will be the positive value of V sub S times I sub S star. So here, if we can find I sub S, or the current that's being supplied to the load by the source, if we can define that or find that as defined here, then we can take the product, the complex product of the voltage phasor of our source times the conjugate of that, and that particular product will produce the complex power supplied by the source. So now what we want to do is determine or find I sub S, the current flowing in this series circuit. And if we look at this circuit, what do we see? Well, we really just see a couple of impedances, the transmission line impedance and the load impedance, and that now gives us a total impedance seen by the source, and we can calculate the current in that way, or we could do a KVL or a mesh analysis and sum up all of the different terms that are connected to this series circuit and that the current I sub S is flowing through. Let's solve it by finding the complex impedance of the entire circuit, or the total impedance, Z sub T. That's the impedance of the transmission line plus the impedance of the load, or that gives us now a total impedance of 80 plus J60 in rectangular form, or we could write it in polar form, and we could rely on a triangle. We have an 80 for the real part, a 60 for the imaginary part. Those are the right, or the sides of our right triangle, and the hypotenuse then gives us the magnitude of the impedance, which in this case is 100, and our angle is then the inverse tangent of the vertical piece, which is in the positive direction, 60, over the horizontal piece, which is 80, and that gives us an angle of 36.87 degrees. So our complex impedance is now found, total complex impedance of 80 plus J60, or 100 over 30 at an angle of 36.87 degrees. And in fact, we probably do want to find the total impedance in polar form, because we are going to use the generalized form of Ohm's law to solve for the current that is being asked or exists in that particular series network. The current, as defined, is I sub S is equal to the voltage being supplied to that circuit, which in our case was 220, and we need to make sure that we're working with the right notation, and in this case it's RMS units. So now we don't have to worry about those factors of 2 floating around. We now have a voltage phasor of 220 at an angle of 0 and a total impedance of 100 at an angle of 36.87. And that, because we represented the impedance in polar form, allows us to compute this rather easily, because now we just have to divide the magnitudes and subtract the angles. So that the source, or the current supplied by the source, is now 2.2 amps, and that's an RMS value or magnitude at an angle of minus 36.87 degrees. We want to now compute the complex power supplied by the source, and we've just learned, or we earlier had made it clear, I hope, that the complex power supplied by the source is the positive value of the voltage phasor of the source, 220 at 0 degrees, times the complex conjugate of the current we just computed, which now the conjugate of that current, since it's in polar form, we just have to switch the sign of the angle, and that will then be 2.2 at an angle of 36.87 degrees. And because these two quantities, voltage and current, are in polar form, it allows us to multiply those rather quickly, and we simply multiply the magnitudes. So we have 220 times 2.2, which is going to give us 484, and we add the angles, which is pretty easy. We're just adding 0 to 36.87. Or we end up then with a complex power supplied by the source equaling 484 at an angle of 36.87, and that has units of volt amperes, and that's supplied by the source. And if we wanted to extract the real power and the reactive power from this complex power, all we have to do is convert from this polar form to rectangular form. Or we take 448 times the cosine of 36.87, and that will give us a real power of 387 0.2, and to obtain the reactive power, we simply take 484 and multiply that times the sine of 36.87. And again, we're dealing with a positive angle, so now we have a positive value for the reactive power, which it has a value of 290.4. And from this, we can now say a little bit more about the characteristic of our particular combination of transmission line impedance and load impedance. As a whole, we now can view this in our complex power triangle, and we can see that Q is positive, and that means what kind of a load do we have? Well, if you did nothing but go back and look at the circuit, as long as those impedances associated with those inductors were positive, you know that you better have an inductive load, and in fact, that's what we have. In this particular case, we've confirmed it, and if we came up with a reactive power that was negative, if the impedances didn't start out negative, we might be starting to question some of the algebra that we had performed, but now we have not, let's say, an inductor load, which it is, but we usually refer to that as an inductive load. The fact that we have a positive Q, reactive power, that now tells us that our load is more inductive than it is capacitive. That's now the complex power supplied by the source. We can separate that into how is that power, complex power, divided or associated with the transmission line and the load line. So let's look at these two pieces of the total load that's being supplied by that source. The complex power of the load, S sub L, is now, is it absorbed or supplied? And we can go back to our diagram, and now the way that we have labeled our voltage, there's our positive sign, which is really the same as being right here. And the current, I sub S, will in fact enter the positive sign of our labeled impedance before it passes through that actual impedance. So the power absorbed, the complex power absorbed by that load is going to be the positive quantity of V sub load times I sub load conjugate. Or we can now say that the complex power of the load is the voltage phasor of the load with a positive sign because of the relationship of our current with the impedance times the complex conjugate of our current going through that load. And I hope it's clear that because this is a series circuit, this particular current is the same as what we just found above, and we then can replace the current going through or labeled as the current of the load is in fact equal to I sub S that we had found that was being supplied by our source. Or we can now find, and we've just convinced ourselves, I think, I hope, that that is now the absorbed power of the load. Let's then work through that. We now have the complex power of our load is the voltage phasor of our load times the complex conjugate of the current I sub S. But we don't know V sub L, but we can rewrite V sub L using the generalized form of Ohm's law. That's simply the impedance of our load, which we do know, that's Z sub capital L, times the current through that load, I sub S, and we do have that, times the complex conjugate of I sub S. Or we now can say, if we remember our facts concerning the product of a complex number times its conjugate, we actually can now rewrite the complex power expression for our load as the impedance of the load, Z sub L, times the magnitude of our current, I sub S, squared. And we'll just show where that comes from if that's not clear, but let's complete this for now. Our load impedance had a real part of 78 and an imaginary part of plus 59. Our current magnitude was 2.2. We square that, and if we compute that quantity, we then have 4.4 squared times 78. That gives us a real power of our load of 377.52. And we then have a reactive power of the load found by taking 2.2 squared and multiplying that by 59, and we then have 285.56 VARs, volt amperes reactive, and if we write all of this as one power, that then has units of volt amperes. And we could, if we wanted to, this is now the power of our load, and this is now the real power, or the average power, and Q sub L is the reactive power. We could also rewrite that in terms of the apparent power, and remember what the apparent power is. That's just the magnitude of the complex power, and we can find that by finding the hypotenuse of this right triangle, or we could then find that as 473.36, which hopefully is the square root of 377.52 squared plus 285.56 squared, and we can find the angle of that complex power, which is the inverse tangent of Q sub L over P sub L, and Q sub L is not quite as big as P sub L, so we hope that when we do that computation on our calculator that we get an angle that's less than 45 degrees. And in fact, it ends up being 37.10 degrees. Again, that's in volt amperes, and this is now our apparent load power. Now, I said that we would try to convince you, if you don't remember, this concept concerning complex numbers. If we had a complex number, let's say A plus JB, and in that sense, we're looking at, in this discussion, we're sort of saying there's I sub S, it's A plus JB, and we want to multiply that by its conjugate or complex conjugate. Now we take that rectangular form, and how do we form the complex conjugate of a rectangular complex quantity? We have the real part stays the same. We simply negate the imaginary component. So now if we look at this product of a complex number times its complex conjugate, in this case what I'm saying is this first piece is like our I sub S, and this second piece was like the conjugate, complex conjugate of that piece. Or now, remembering from wherever you learned this, we now have four terms in this product. We have the first two terms, A times itself, so we have A squared. Then we have the cross terms. We can now say that let me just sort of label these out. So we've now just found those two. Suppose now we do these two, so that now we end up with plus JBA. Then we have to do the other two, or multiply the first two by the minus JB. We have A times minus JB, and you could say then we have, in this case, a minus JBA, and finally we have the last two terms, which is then JB times minus JB, or we could write that as minus J squared times B squared. So remember that we now, and what do we see? Now hopefully you can see that this JBA and minus JBA cancel, and we're left now with this product of a complex number times its complex conjugate, leaving us with A squared, and we have J squared, which is minus 1, times, or negated, so we now have A squared plus B squared, and in fact, that's now, in our case, simply the magnitude of our original complex number squared. The magnitude of I sub s, remember, that would just be the square root of A squared plus B squared, so that now I sub s squared is now A squared plus B squared. Just squaring that. So that's the aside that I had promised. And now we can do a few more things relative to this example. We've computed the complex power of the load, and this is absorbed. Maybe I should say that. That's now the complex power absorbed by the load. We can also find the power factor of the load. And what do we know? Well, if you forget, you can always say that the real power of the load, P sub L, is now V sub L, I sub L, cosine of theta sub L. And remember, this I sub L in this particular case, because of the series circuit, is just I sub L. Or we now have the fact that this cosine of theta sub L is the power factor of the load, so that now we have the power factor of the load we can determine because we know the real power of the load, P sub L, and we know the apparent power, which is the product of V magnitude times I magnitude. And that's now this cosine of theta sub L. And theta sub L, from our earlier conversion from the rectangular to the polar, is now given to us by 37.1 degrees. So that's now the angle of our load power. We now have this is equal to the cosine of 37.1 degrees, or we now have a power factor of the load equaling the cosine of 37.1, which, if we perform that calculation, we obtain 0.798. And because it was Q was positive, we had an inductive load, and an inductive load, the current lags the voltage. And now we have produced most of the information that we would need relative to the load properties of that particular circuit. Now, one more thing that we could do is we could look at or find the complex power of the transmission line. And we could do that exactly the way we did the complex power of the load, but let's do it a little differently. What do we know? We know the total complex power being supplied. We know the complex power of the load. We know that the difference of those has to equal the remaining power in the system, and that's the transmission line power. Or we now know that the complex power of the transmission line, S sub lowercase l, is equal to the supplied power, S sub S of the source, minus the complex power of the load. And now, since we're doing a subtraction of complex powers, it's usually cleaner to do that when our complex values or quantities are written in rectangular form. We now have 387.2 plus J 290.4 minus the load power, which was 377.52 plus J 285.56. And that now ends up resulting with a transmission line complex power of 9.68 watts plus J 4.84 volt amperes reactive, or if we keep them both together, that's now 9.68 plus J 4.84 volt amperes. And two more things that we can just make sure that we know or can compute. We've actually already found this value, but let's just go ahead and write it down. The apparent power of the source, how much apparent power is being asked by the source, that's now the source voltage magnitude times the magnitude of the current in that system. And we know that we were starting with a source voltage magnitude of 220. We computed the magnitude of our current to be 2.2. So the apparent power of our source is 484. We also found the angle associated with that complex power by converting that source power from rectangular form to polar form. And once we have the polar form, we have the angle, and the angle quickly allows us to find the power factor of the source. The power factor of the source is now the cosine of that angle of the complex power of the source. Or we now have cosine, and now do we need to worry about the sine, S-I-G-N, of that angle theta sub S? We know the angle was actually a positive 36.87, and that now allows us to conclude that we have, if we take the cosine of 36.87, that would give us 0.8. If we took the cosine of minus 36.87, that would also give us 0.8. That's why we need a little bit more description to convey what the power factor actually is. And the remaining piece of information that we use is the fact that this particular angle was positive to begin with. And knowing that allows us then to state that our power factor of the source was a lagging power factor, and it had a value of 0.8. So the power factor of the source is 0.8 lagging.